The nice thing about section 10.2 is that at least at the beginning it's all review. This is something that you already learned way back in chapter 1.
We learned the equation of a circle, and at that time you actually memorized the equation of a circle, and it was x squared plus y squared equals r squared. And the tricky part then, I reminded you over and over because it is tricky. Remember, this is r squared. Don't think that this is r. If you have a circle centered at the origin with a radius of 4, say, then 4 squared is 16. You'd have x squared plus y squared equals 16. Great. What if you want to transform that circle? What if you want it to be centered at hk? Well, then you put in the h and the k, and it moves like that. What they will typically do is they'll give you some formula and you look and you think, this doesn't look anything like this. No, it doesn't. You have to complete square. The trick is there's an x squared and there's a y squared. All of the conic sections except for the parabola have both the variables squared. And so if they're both squared, well, then you have to complete the square twice. And so here, they've taken the x squared and they've put like terms near each other. Here's your minus 16x. And then there's a y squared that's here, and there's a 14y. And we don't want this thing move it to the other side. And then you set it up, and I don't think theirs is as pretty as mine because I put parentheses so I know what's going on, and I put plus with a line, and I put plus with a line so that I know what I have to do and I don't skip any steps. You take half of negative 16 and you get negative 8, and you put negative 8 squared right here. And you put negative 8 squared right here. And then you take half of 14, it's 7. You put 7 squared right here, and you put 7 squared right here. And these add up. Here they've written 64. That kind of spoils the fun. If you know this is negative 8 squared, then you can just copy the negative 8 right here, and you don't have to undo the 64. On this side, yeah, you'll do the 64. But on this side, why write it that way? It's just an extra step. So there's your negative 8 squared that I mentioned, and here's your 7 squared that I mentioned. And now we know, oh, there's the h minus h, so h is 8. Plus 7 is minus k, so k must be negative 7. And here they've shown it to you. There's a minus, subtract the h, subtract the k. There's h, there's k, that's the center. What's the radius? It's the square root of this, which happens to be 9. And so, yeah, there you go. And that's how circles go, and that should feel vaguely familiar. If we want to define a circle as a shape, and I guess we should, when we had the parabola, what we said was there is a point, which is called the focus, and there is another line, which is called the directrix, and all the points that are the same distance from the directrix and the focus are points on the parabola. And that's how we defined a parabola as a shape, using those two things, the directrix and the focus, to orient us. Here, we only really have one thing that I almost want to call it a focus, but it's not. It's the center. It's kind of like a focus. So there's your HK, it's the center, and then there's a certain distance, and the circle is the set of all the points that are at a fixed distance. And so the parabola, it wasn't a fixed distance, it just had to be the same distance to the focus, and the same distance to the directrix, and every point that had the same distance to each of those. Here, the distance never changes. It's always r, whatever that is, and this point is r away, and this point is r away, and this point is r away, and so on and so on and so on. And that's in your notes. A long, long time ago we talked about that. I think I even derived the formula of the circle using the Euclidean distance formula. So anyway, that's circles, and that's a review, so let's go on. Here come ellipses. So we've studied the parabola, we've studied the circle. Here comes a third sort of conic section, and this is called the ellipse. Think of it as an oval shape. Ellipse is kind of a fancier word. So what's an ellipse? The ellipse is interesting because it has two focuses, and we don't like saying focuses. If we speak Latin, we like to say foci, which of course is nonsense because the Latins did not pronounce the C ever as an S or the I ever as an I, but the English pronunciation of the Latin plural of focus is foci. And so get used to it, because ellipses have two focuses, they have two foci. And so I'll say foci a lot for the next little while. And I hope you do get used to it. So here's an example. There's the first foci, and we've labeled it number 1, so it's F1. And here's the second foci, the first focus and the second focus. So 2 foci, and this second focus, since it's the second, we call it F for focus and 2, and that's very, very nice. Then how do we define the thing? Well, here's a drawing, and you may have done this like in the 3rd or 4th grade. I've known students that did it, and a lot of students look at it and say, nope, never did it. And if you've never done it, I encourage you to Google, go to YouTube and Google draw an ellipse, and they'll show you how to do this. And the easy way is you use a piece of corrugated cardboard. They're using a fancy green, a self-healing mat, they call them if you're an art person, and you might have one if you're an art person. But otherwise, find an old piece of cardboard. It's bumpy enough. And find a couple thumbtacks and poke the thumbtacks in 2 locations, and those are your foci, your 2 focuses. And then get a piece of string of some length, and you tie, they attach a piece of string to the tacks, and what happens is you run out of string. That's all right. We can explain it this way. When you go on YouTube, they'll tell you to double the length of the string and loop around here and then pull it tight. But anyway, you pull it tight. That means there's some distance from focus number 1, and so call it D1. There's some distance from focus number 2, so call it D2. And what is an ellipse? An ellipse is the shape you get if D1 plus D2, the sum of the distances, is constant. And so you get these 2 distances, and you add them together, D1 plus D2, and how long is that? Well, it's the length of your string. And what if you pulled the string over here with your pencil? Well, then D1 is a lot longer. Yes, and D2 is a lot shorter. And so D1 plus D2, well, it still has to be the length of your string. And over here, the same thing, and over here, the same thing. And if you loop your string over on this side, you get the same idea. And everywhere you go, you get how far are you away? You are the sum of those 2 distances, which is the length of your string. So what is an ellipse? It's the set of all points in a plane, the points whose sum of the distances from the 2 foci is constant. And there is a center of an ellipse. It's the midpoint between the 2 foci. So here's focus 1 and here's focus 2, and exactly halfway between where my cursor is, you can see it, and that's where the center of the ellipse is. So let's look at this little drawing, and it has more things labeled because there's a few more vocabulary words we need to learn. Here's a focus. The first focus is here. The second focus is here. Halfway in between is the center. And where is the center? Well, if you look at the XY axis, this is centered on the origin, and so 0, 0 is the center. And so this is some distance away, let's call it C, and this is some distance away in the other direction, and so let's call it negative C. And so those are the names of the 2 points for the foci, negative C0 and C0, if your ellipse is centered on the origin, 0, 0. Then, if you look at the ellipse, it is not round. There is one length, sideways I'd say, that is longer than the other length. So the horizontal distance seems to be bigger than the vertical distance on this particular ellipse, and you think, well, I could draw it a different way, and yes, you could, but on this one, we call the distance, the long distance, the major axis. It goes from a distance of A to the right of the origin to a distance of A to the left of the origin, and so it has points negative A0 and A0, and that seems to make sense. What about this other line, the shorter line through the center? We call that the minor axis. and it goes from 0, b, so 0 because it hasn't moved off the x, and b, that's the distance in the y direction, and then negative b, the same distance in the other direction. Vertices, so these 2 points at the ends of the major axis are called the vertices, which is the plural of vertex. So a parabola we saw in 10.1 has a vertex. This has 2 vertexes, and we call those vertices. That's the plural. Okay, so some vocabulary, and feel free to flip back as you need to. I encourage you very much, and I haven't done so just because the technology is wrestling with me tonight, but I do draw this in the class and I label everything. And I haven't done that, but I encourage you in your own notes for your own benefit to draw it, because watching me do something, it goes in and it goes out, and you don't remember things. And if you draw it yourself and label the different parts, then you'll get a better understanding of it. What are we coming up to? We're coming up to formulas. And this happens to be, well, let me go back to this. You can actually do it, and I have done it in the past, and the kids never enjoy it as much as I enjoy it, but you can derive the formula for an ellipse from this. If you know what C is, and you know what these things are, and you know this definition, the distance have to add up, and you could do it. The book doesn't. It gets kind of hairy, and that's why I say I enjoy it more than the kids. Here's the formula for an ellipse, and I want you to notice what this looks like. This is a horizontal ellipse. The major axis is horizontal, the long direction. Contrast that with a vertical ellipse where the major axis goes on the y-axis. If it's major axis horizontal, it's going left to right, then the x has a bigger denominator. So you'll always be able to spot these because this a, which is the distance to the vertex, is bigger than b, which is the distance to the, and it's really annoying because these 2 points don't have a name. This is a vertex, this is a vertex. These 2 points at the ends, the 2 ends of the minor axis, are called the ends of the minor axis. And so there's not a little word you can say. You could, if you didn't want to ever say the word vertex, you take a vow. I will never say vertex. Vertex will never leave my lips. You could call these the end points of the major axis, but no one does because it's too many syllables. I'm not sure why they didn't come up with another name. I'm sure someone somewhere does have a name. And in fact, there are some other things about the ellipse that are named, and they used to be taught like your grandparents' day, but they're not anymore. The A is bigger because it is on the major axis. It is one of the vertices, one of the vertex locations, and so there's the vertex. Anyway, and then the Y is smaller, the B is smaller. So big number in the big direction, small number in the small direction, and then there's an equals, and there's a 1. And I'm hoping you are taking notes. Make sure that you draw a big arrow here and you say, this must be 1. It has to be 1. If you have an equation and it says equal 7, then you're not done. It might be the formula for an ellipse, but it is not a standard equation. So the standard equation of an ellipse always has a 1 here. Always has a 1 here. And the whole idea here is the thing that's bigger, well, what's it under? It's under the x. Oh, then the big direction, the long direction, is in the x direction. If your major axis is vertical, well, then what's bigger? Well, the a here is bigger, and the bigger is under the y, and so, okay, your vertices are these, and you see where the y is, the a is, it's the y instead of the x. So you can do this fancy stuff and say A is bigger than B is bigger than, they both have to be positive, obviously. You can't have a negative. What would it mean to say, well, I'm 3 inches in the negative direction? Well, that doesn't make sense if you're doing that. How far is the vertex from the center? -3. Well, it can't be. You can go in the negative direction, but you can't have a distance. So these A's and B's are distances, and so they do have to be positive. And the big one, this annoys me a little bit. I get a little frustrated. You've seen me teach in class, and this feels so different from it. And if I were in class, I would be doing all of this just on the fly. I would walk in and I'd pull one of those markers out of my pocket and I would start writing, and I would do all of this without referring to any notes. And I like to teach that way. And the first time I taught conic sections, I had no idea how to do it because I hadn't been taught conic sections carefully as a child. By the way, I'll mention Boise State in their algebra class doesn't even do conic sections. So the one or two of you, I'm talking to you, Val, the one or two of you who are going on to some years of calculus when you get to 175, actually it's 175 and then it's 275 again. When they start talking about conic sections, you'll say, oh yeah, got it. And you'll look over at your classmates who are BSU alumni, and they will all look confused because they don't do this in their course at all. But anyway, the point I was making was these things are complicated. Look at all these details. It's like, what? And I don't like with a piece of paper in my hand where I'm reading stuff off because I'm asking students to learn something so well that they can just do it. And if I have to cheat and use a piece of paper to refer to, how can I ask my students to understand something that I don't understand to that level? So I figured out all these things. I just looked, this is what mathematicians do for a living, is you look at stuff and you find the pattern. And the pattern I found is that whichever of these two numbers, whichever of these two denominators is bigger, that tells you the direction. So if the thing under the X is bigger, it's a horizontal. And if the thing under the Y is bigger, then it's a vertical. And does it matter what name you call it? No, it doesn't matter at all. You don't have to remember this A, B, blah, blah, blah. Just remember the big number is the one telling you the direction. And then if it's an X, right, well, then that big number's square root, the square root of A squared, has to be in the X position. And the square root of the smaller number has to be in the Y position. Why? Because it's under the Y. And over here, the same pattern exists. And I think it confuses things to say, well, it's an A and it's a B, and sometimes it's a B and then it's an A, and it gets confusing. Where are the foci? So the foci are a little bit interesting. Well, let me back up just a second. Notice, and this is something else, draw a big arrow, these are squares, right? This is A squared, and your vertices are at A and negative A. This is B squared, and the endpoints of your minor axis are at B and negative B. And don't forget that these are squares. That's another way that students can go wrong. Okay, the foci. This is an interesting formula. C squared equals A squared minus B squared. And so if you want to know what this C is, you take this A squared and you subtract this B squared and you get C squared. Take the square root. Now you know what C is, and that's where your focus is. And there's another focus in the other direction from the center. So how do I remember this? Because in theory, you have to memorize this. The way I remember it is this has a plus and this has a minus. And you're thinking, well, how am I supposed to remember that this has a plus? And so you're going to laugh. This actually isn't as bad as the gorillas and the bumblebee, but you might laugh. I remember this as a plus because this is an E plus. And you think, it's not an E plus, it's an ellipse. And I say, okay, so the letters are in a different order, but you can call it an E plus instead of an ellipse, and it almost sounds the same. So the formula for an E plus, for an ellipse, has a plus in it, and the focus always has the opposite symbol. And so if this has a plus for the formula, has a minus for the focus. And we will work one of these in a minute, and you'll see how it kind of goes together. There are several in the book, and I don't want to cheat you out of the enjoyment. I know you kids are smart enough to read those and to understand them, and so I invite you to do so. There's another one. What if the center of the ellipse is not at the origin, but it's at some point HK? Well, then you do what you do. X turns into X minus H, and Y turns into Y minus K. And wait, this is nothing new. This is the exact same thing as before. If you translate it to HK, if you transform it, then you have to subtract this off. Great. Well, then what happens to your vertex? Your vertex was originally negative A, 0, and A, 0, but you have to add the H and add the K. You have to add the H and add the K, and so everything just works. And what about the minor axis? Well, why don't they put the points in? I don't know why they don't put the points in. They should put the points in. You could figure it out. I'll let you figure it out for yourself. How about the focus? Well, it should be negative C, 0, and C, 0, except there's an H and a K, H and a K. And how do you figure out where the focus is? You take A squared minus B squared, and yeah. So there's kind of nothing new there. How do you do this? Typically, you complete the square. And so I will let you read one like this yourself, and let's work our own just for the thrill of it. You know how much I love completing squares, and this is especially thrilling because I get to do it twice. Before we get to that, let me just talk about applications. So I mentioned the Capitol building of the United States, and there it is. It is a elliptical ceiling. Here's an ellipse. Notice there's focus 1 on the left and there's focus 2 on the right. If you put an emitter on focus 1, so rays come out. And what are these rays? They're light waves, or they are sound waves, or they are radio waves, or they are shock waves. They're some kind of rays, they're waves, and they're coming out from here. And if this elliptical shape is reflective so that the rays bounce off, then no matter what direction the ray comes out, and typically sources come out in all different directions, right? So here's this source, this emitter, and it's coming out in all different directions. No matter what direction it comes out, when it bounces off the ellipse, it always goes through the other focus. So if this is the emitter and you have this as whatever you want it to hit, that works really, really well. And so they give you several examples, and I won't turn to them yet because I want to refer to this drawing. But one example is the elliptical ceiling of the House of Representatives. And so if you are sitting at a desk right here and you have a secret that you want to tell your colleague and you whisper it to them, well, those are sound waves coming out of your mouth, and those sound waves go in every direction, and when they bounce off the ceiling of this elliptical ceiling, when they bounce off the ceiling, they all go, no matter which direction they start, they all end up at this focus. And so if someone whispers to their colleague here and you are sitting right here, it is as if they are whispering to you. And I want to say it's John Adams who figured this out, and so he put his desk at a place where he could listen to the other side of the chamber. And so he's in one party and wants certain things done, and here's his opponents, and they're whispering and they're saying, there's no way we would ever vote for this unless they were willing to be the minimum we could take, right? And then John Adams stands up on the floor and he says, I propose that as a concession to our colleagues, and then he gives them that minimum, and well, they go along with it. He says, well, okay. And because he knew, because he overheard so many conversations. So great story there. St. Paul's Cathedral is like this. If you've ever gone to the Tabernacle building, the Salt Lake, there's a church down there, the Church of Jesus Christ of Latter-day Saints. You can go to Salt Lake and get a tour of Temple Square, and there's this fabulous old wooden building, and it is elliptical. Yeah, it's elliptical. And as part of the demonstration, there's this cute gal that stands up here. At least when I went, it was a cute gal, and she stands up here and she has this wooden kind of a box, and she's sitting here, and you are sitting back in the audience in one of the pews. I think they're just chairs, not pews. It's been a while since I went. And she drops a pin on it, and the pin falls on this box, and it goes dunk, 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 and makes a little tiny noise because it's a pin. And you sitting, 20 rows back, wherever it is, can hear it just plain as day. It's like you are sitting right there, and it's astonishing. I mean, audibly astonishing that you kind of like, what? Huh? It's amazing how it works, and math at work. Okay, third example. Suppose you have kidney stones. I can remember I had kidney stones once. Um, it was the worst pain I've ever been in. They say that it's actually only pain that's worse than childbirth. Sorry, women. Females are known for their toughness, their ruggedness, their. Oh wow. Sorry, there's a big bug on my. Huh. It's on me. Whoa. That would be fun for the kids hearing the recording later. I think it was a spider. I don't know where it went. Okay. It was crawling up the side of my monitor here. Yeah. Well, I'll find him later. I hope I don't find him when he's crawling up my leg. Anyway, where was I? I had kidney stones once, and they're considered to be a very, very severe pain. If you've ever had kidney stones, you know what that's like. It hurts a lot in your kidneys, right? So what do you do if you have kidney stones? Well, what you do, my dad, when he was young, um, he's old now, but when he was younger, when he was in his 20s or 30s, he had kidney stones, and he went into the hospital, and they cut him open, and they cut open his kidney, and they took out the stones, and they sewed his kidney back up, and they sewed him back up, and he sat in the hospital for 2 or 3 weeks, because that's what happens if you have kidney surgery. So here's the cool idea. You get an elliptical tank of water. So the tank of water, and this is the wall of this big giant bathtub, say. And right here is an emitter, and I'll describe it in a second. And right here is your kidney. And you're thinking, what? Wait, what? Yes, what they do is they draw little lines on you. They use an ultrascan to locate your kidney very nicely, and they use a magic marker, a Sharpie, and they draw on you so that they know where your kidney is inside your body. And then they have you sit at one end of the tank, and there are little laser lights that don't have any effect other than, well, they're lights, and so you can aim, and they line up the dots, the lines that they've drawn on your skin with the lights from these lasers, and so they know exactly where your kidney is, and they say, hold still, don't move, and there's a little strap to keep you located there. Well, your kidney is at this focus. What happens at this emitter? This emitter is a little, it's a little like a shock wave. So here I'm hitting my hand. If you hear this noise, and it just like that, and it vibrates the water. And what happens to those vibrations? They bounce off the sides of this elliptical tank. And what that does then is they all focus, because what happens to these waves? They're sound waves, right? Sound waves. And they go through water as waves. They're vibrating the water, and they all end up at your kidney, and they vibrate. And they go. And what they do, these little tiny fast sound waves beat the heck out of your kidney stones and break them up, and then you can pass them out through your urethra. And that's also painful, but it's nothing like surgery. I mean, people go in for this, and it takes a little bit of time, and then they go home for the afternoon. And over the next few days, they pass out the stones, and if they go in again, they can. But what a cool. Yes, it's total, definitely a wow. Oh, Val gets kidney stones all the time. Yeah, they're horrible. I can remember being in the emergency room, and it's the sort of pain where you flip over on your left side, and no, it still kind of hurts, and so you flip over on your right side, and then you think you should sit up a little bit, and then you think you should lie back down, and then you think you should curl your legs one way, and it was like watching a fish that had landed on the bank, the way I'm flipping around on this journey trying to get in a comfortable position, and there wasn't one. We get home, and the next day my wife says, because what happened there? And the nurse says, so what's your social security number? How old are you? What's your date of birth? and asking me all these questions. And I come home and my wife says, no, it's the first time I've ever seen you rude to someone. Evidently, and I don't have very clear memories, but evidently I kind of snarled at this lovely nurse who was just trying to do her. What's your date of birth? It's September yeah, that was me. There you go. This is called, by the way, lithotripty. Litho means stone, and tripty means, look it up, it's Greek. They tell you this. Yes, a lithotripter. And it just uses a shock wave and it pulses. I like the ones in the water better, but there you go. Another ellipse that you may have heard of is the Earth. And you think Earth isn't an ellipse. Earth is an oblate spheroid. Yes, Earth is not a sphere. It's an oblate spheroid, which means it's just a little fatter at the equator than it is north to south pole. But no, where the ellipse comes in is we are an elliptical orbit. The Earth is not in a round orbit. This drawing, by the way, is extremely exaggerated. The orbits look like this. You look at this and you say, oh, wow, it is an ellipse. If you actually saw a drawing of it, and if it were printed at this scale, you wouldn't be able to tell that it wasn't a circle. It has just a very slight eccentricity. It's only a little bit elliptical. And where is the sun? Well, if we had a circular orbit, then the sun would be at the center, but the sun isn't at the center. We don't have a circular orbit. We have an elliptical orbit, and the sun is at one of the two foci of our orbit. So that's kind of interesting. I get off on this stuff. By the way, just so you know, how can you tell something is a circle? Well, the x squared and the y squared have the same coefficient. And here they're all 1. And it's like, well, that's not very interesting. And how do you tell that something with an x squared and a y squared isn't a circle? If it's an ellipse, well, then the two coefficients are different. This has a 16 and this has a 4. And if you look at it, you think, wait a second, this isn't even standard form. No, it's not standard form because you're not supposed to equal 64. You have to equal 1. And so to make this a 1, divide it by 64. And then whatever you do to the left, do to the right, whatever you do to the right, do to the left. So divide this by 64. Well, you get 1/4. And divide this by 64, you get 1/16. Now you have x squared over 4 plus y squared over 16. Oh, there's your a squared and your b squared. And you say, which one's, well, x squared is on top of a 4, and y squared is on top of a 16. Oh, 16 is bigger, so the up and down, this is a vertical. This is a vertical ellipse. And you could figure out what b is. Well, it's the square root of 16. Oh, it's 4. You could figure out what, sorry, this is a, I get the way they name it. I just call it the long one. The long one is the square root of 16, and the short one is the square root of 4. And then you look at this drawing and you think, oh, so the square root of 16 is 4, and the square root of 4 is 2, and there's 2. Oh, this is the drawing. It's vertical, and that matches. And that's what this problem is supposed to be, is match. And you should be able to just look and you can match them. Okay, let's pick one of these. Here I go. This is number 43. 4x squared plus 9y squared. Notice this plus. That means it's any plus. It's an ellipse. 4x squared plus 9y squared minus 16x plus 18y minus 11. What I'm going to do first is separate out the stuff. So I want all my x's together. I want all my y's together. I want the stuff that's not x and y over on the other side. And so here I go, 4x squared. And I like to check them off. And here's a minus 16x. And then I'm leaving some space. There's a plus. And then I'm going to have a plus 9y squared. I got that one. I have a plus 18y. I got that one. I have a plus something. I don't know what it is. Equals, I'm moving my 11 to the other side. So there's my equals 11. We are ready to complete the squares. So half of 16, hold up, hold up, hold up. Remember, and you might not because it's been a while. It was chapter 3 that we completed squares, and that was some time ago. You cannot complete the square if you have a coefficient in front of your x squared. So here's a 4. This 4 means you can't complete the square. And over here in front of the y squared, there's a 9. You can't complete the square. What you have to do, is factor those out. So I'm pulling 4. I get x squared minus 4x plus something plus, I'm going to factor out the 9. 9y squared plus 2y plus something. And this is why I love the way I teach completing the square is, what do I have to add? 4 times this. And so let the notation do the work. You've heard that saying of mine. It's a really, really good one. Let the notation do the work. Make these hard. Plus 9 times the other thing. I don't know what it is. I'm saying half of negative 4 divided by 2 equals negative 2. So here comes a negative 2 squared. And here 2y divided by 2, half of it equals 1. Here's a 1 squared. Oh, I did it wrong, didn't I? Because as soon as I write the negative 2 squared, I'm supposed to put it over here. Negative 2 squared. And here's the 1 squared. There's the 1 squared. Here's 4. There's my 4 times, and I don't have much work, right? Because the notation does the work. There's a negative 2 in there, squared. And here's a 9. And again, most of my work is done. I just copy stuff. Y plus 1 squared equals, and now I have to figure this out. This is 11. This is minus 8. This is plus 9. I'm thinking 11 minus 8 is 3 plus 9. I'm thinking this is 12. Well, this has to be 1. Must be 1. So what am I going to do? I'm going to divide by 12. I'm going to divide by back up, Gary. This is a 2 squared equals 4. And so this is all wrong. This is all wrong. This is 11 plus 4 times 4, 16, plus 9. I'm thinking this is 36. So here's a 36. The 36 must be 1. So I'm going to divide by 36. I'm going to divide by 36 in front of my y. My stylus is doing something strange. What do I end up with? I get x minus 2 squared over 9, because 4 goes into 36 9 times, plus y plus 1 squared over 9 goes into 36 4 times equals 1. This is the standard form of an ellipse. And I can see my h. Let me write all this stuff in. H equals 2. K equals negative 1, because there's an x minus h and a y minus k. Watch out for the signs, right? A squared, this is the bigger one, equals 9. B squared equals 4. What does that mean? That means A equals 3. That means that B equals 2. I just took the square roots. That wasn't a big problem. And where is my center? My center is at 2, negative 1. And so 2, negative 1, center, 2, negative 1. And the the vertices are 2, negative 1, but the x moves over. The x moves over 3. It moves to the left 3. 2 minus 3. And what's the other one? 2 plus 3. And where are the endpoints of the minor axis? Endpoints of minor axis. Well, they're at 2, -1, except you move over 2. So you have 2, -1, 2. And obviously, these don't quite look like points. 2, -1, +2. You can convert this one to a -1, -1. You can convert this one to a 5, -1. You can convert this to a 2, -3. You can convert this to a 2, +1. Where are the foci? We need foci. We better get a different color. Foci are in red today. Foci. Oh, my cursor is doing strange things. C squared equals A squared. It's the opposite sign. This had a plus for the standard equation, and so there's that. So C squared equals A squared is 9. I'm just copying from what's down below. Minus B squared is 4. So C squared equals 5. That means C equals the square root of 5. And that means my foci, where are they? Well, they're at the center, except they're shifted by the square root of 5. And so I'm going to have 2, -1, but it'll be 2 minus the square root of 5, -1, and 2 plus the square root of 5, -1. Wow. We fit it all in this little whiteboard. I don't know if that was fun or if that told you everything you wanted to know. Some words appeared here, and I don't know if it was me or one of you, but I was going to draw this, but it would be easy enough to sketch if you had some graph paper or just wanted to sketch it yourself. You know where the center is, you know where the 2 major axis endpoints are, you know where the 2 minor axis endpoints are. You can draw the foci just to verify that you're in the right place. What's the square root of 5? It's like 2.36, so 2 1/4. And so you can figure out where these points are approximately. Wait, I messed it up. Why is there a comma right here? There's no comma right there. Let me fix the comma. Comma. Bye-bye, comma. Okay, I got rid of the comma. So 2, so like 4 1/4, and this is about 3/4 and -1. Anyway, you could sketch the thing, and these are all the locations, and then you could key this into Desmos and see if it came out right, and that would be a way to check it. So there's the idea of vertices. So if we're at the top of 735, doing one like this, it almost looks harder. I'm thinking of a ellipse, and it has vertices at 0, -8, and 0, 8, and the length of the minor axis is 10. What's the formula for it? Well, the way to do this is to sketch it. And so get an XY plane, and you just, scribble that, and then you see where 0, -8 is. Well, 0, -8 is down here somewhere, and 0, 8 is up here somewhere. Oh, those are the vertices. Well, then it's a vertical. It's an up and down ellipse, and the length of the minor axis is 10. That means you go out 5 and you go back -5. And now you know your A, you know your B. You can figure out your C, because C squared equals A squared minus B squared. And then it's just a matter of writing the thing down. In fact, you don't even need C to do that. If you know A and B, you can do it almost in your head if you practiced it a little bit.